On our last video, we ended with the revealing of Einstein's famous equation, E equals mc squared. That is a useful equation. It can tell us, given a certain amount of mass, how much energy we could get out of that mass if we were able to convert it directly into energy. There's an idea that mass and energy are actually the same thing, which sounds very weird. We've been treating them differently all year, but it turns out that they must be the same thing. They can be converted from one to the other, so now we talk about mass energy. Our first example, practicing using this equation. How much energy is stored in 1 kilogram of matter? We go to E equals mc squared. The mass has to be in kilograms, and it is, so 1 kilogram. Speed of light is on the reference table. It's 3 times 10 to the 8th meters per second squared. Please don't forget to square it. I'll give you a second to do this math right now, but it turns out that this energy is 9 times 10 to the 16th joules. Now, you probably don't have a good grasp of how much energy that is. Let me fill you in. Picture the most violent volcanic explosion that we've ever had. You might have heard of Mount St. Helens. Bigger than that. You might have heard of Vesuvius, buried in the town of Pompeii 2,000 years ago. Bigger than that. This is about the energy involved in the explosion of the volcano Krakatoa in Indonesia. This is the, I think, biggest one in recorded history. You could hear this explosion like thousands of miles away. Krakatoa is in Indonesia. You could hear this in Australia, like across the ocean. So this is as much energy, about as much energy as the most violent volcanic explosion in recorded history. Seems insane. 1 kilogram, to remind you, is this little brass mass right here. This is 1 kilogram. This much mass, if you were able to turn this much mass into its other form, energy, would have enough energy to be equivalent to a huge, enormous volcanic explosion. That is, at the very least, very surprising. And that is not a result I necessarily would have expected. I'm not going to use green. Green isn't showing well. Let's see. I want to switch markers on you guys. Let's do purple. I haven't broken out a purple in a while. Come on. There we go. Okay. Technical difficulties. So, a tiny little bit of mass has a lot of energy packed into it. Let's go to a second example. Back in 2008, the world used approximately 5.2 times 10 to the 20th joules of energy. Bigger than this. Let's see how much bigger. What is the equivalent of this much energy in mass? E equals mc squared. 5.2 times 10 to the 20th joules equals m. 3 times 10 to the 8th meters per second squared. Now, please, you have to write this out. You cannot skip right to squaring this. You can't just plug in 9 times 10 to the 16th. Don't do that. Write this number out, put the squared sign, then do the math. I've seen people do that and lose points before. If you want to take a second, pause and do the math. It turns out that this mass is equal to 5,778 kilograms. That's a lot of mass. We're talking maybe, well, hold on, let's see kilograms. So we've got people are about, what, 50, 60, 70, 80 kilograms. We're talking the weight or the mass of maybe 70 or 80 people. I'll tell you what is actually this much mass. This, according to my research, is less than the mass of 1 elephant. Elephants are pretty big. I'm thinking like the real big elephants, African elephants, okay? Alive in the bush, all the way down there on the plains in the Serengeti. If you were to take less than the mass of 1 big elephant, if you were able to turn all that mass, if all turned into energy, could power the world for 1 year. That's incredible. I am not advocating sacrificing elephants for this purpose, but the fact that that little mass could provide all the energy that we need, and probably some left over, is astounding. Mass is just a super concentrated form of energy. It's very, very weird and very interesting. I've got two more examples, both of which are important because they involve what you see on the reference tables, which I think is kind of confusing if you don't have this lead-in, where we talk about universal mass units and everything. We already did how much energy is stored in 1 kilogram. Now we're going to do how much energy is stored in 1 universal mass unit. So you might say, oh, well, easy. We plug it into the equation, E equals mc squared, and we go on our way. It's not that simple, unfortunately. Okay? It is not exactly that simple. That equation, E equals mc squared, only works if you are using kilograms. That's the only way it works. So, this is a unit of mass. The first thing we would need to do is convert it to kilograms. Then we can put it in formula. And we get an answer in joules. But this is a really tiny amount of mass. It's going to give a really tiny amount of energy. A joule is too big. We need a smaller unit of energy. We will reintroduce now the electron volt. We're going to end up converting this back to electron volts. That's our process. That's how we're going to figure out how much energy is stored. The formula will tell us the answer, the energy in joules. We will find the energy in electron volts. So, let's get started. I have 1U. The conversion between universal mass unit and kilograms is on the front. I guess you probably didn't even really need to have to do this, because we know 1U is just equal to this number. That's 10 to the negative 27th kilograms. Now we can plug that into E equals mc squared. We can figure out the energy. 1.66 times 10 to the negative 27 kilograms times 3 times 10 to the 8th meters per second squared. I'll give you a minute. You can pause and do the calculation. When you are done with that, the energy created or released by turning that mass into energy is equal to 1.9494 times 10 to the negative 10 joules. And like I said, we want to convert this into electron volts, because that's a really tiny amount of joules. We want to convert it into a number that's not so tiny. Your reference tables tell you that 1 joule, I had it wrong. 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. When you convert, you end up with this answer. 9.31 times 10 to the 8th electron volts. That is how many electron volts of energy are present in 1U, basically a proton. Like almost a billion electron volts. It's a huge number. We're going to do something with this number, because this is not quite the way it looks on the reference tables. We're going to take this number, 9.31 times 10 to the 8th EV, and we're going to do something weird to it that it wouldn't normally do. Let's move that decimal place over and say that it's 931. We made this number bigger. In order to keep the meaning the same, we got to make this smaller. How many times smaller? We moved the decimal point 2 times. We got to make this 2 numbers smaller. Let's do 9.31 times 10 to the 6th EVs. And we're going to go one step farther. On your reference tables, as we talked about on almost the very first day of school, there is, this is all covering everything, there is a chart for prefixes. 10 to the 6th is on there. 10 to the 6th is known as mega. So instead of writing 931 times 10 to the 6th, here's what I'm going to do. I'm going to replace that 10 to the 6th with mega, and I'm going to say that this is equivalent to 931 mega electron volts. So, all of my hard work has gone from taking this much mass and converting it to this much energy. I think that's a really weird conversion if you are not exposed to it in this way. But it shows up on the reference table just like this. I'll show you where. I'm going to erase some of this. one universal mass unit, as written on the reference tables right here, is equal to 9.31 times 10 to the second. So 9.31 times 100 is 931. I think if you don't go through that explanation, it's a really weird conversion, you might miss it. But that is another way that you can convert mass into energy. Notice, this is for converting universal mass units. The equation that we were using earlier, E equals mc squared, is used for converting amounts of mass in kilograms. So if you're given a mass in kilograms, use the equation. If you're given a mass in universal mass units, use the conversion. If you don't use the conversion, you have to go through this whole big mess that we just did right here, trying to save you some work. Okay? So, a last example. Let's put this to use. We just saw that when helium is created from 2 protons and 2 neutrons, it has a nuclear mass, a mass of the nucleus of 4.0015 U. How much energy is released when helium forms? So I mentioned, and you can go and look at this, it's on the front, that this thing called that mass difference, or the mass defect, whatever you want to call it, it really means the difference in mass between the reactants, the individual protons and neutrons, and the end product, the helium nucleus. The mass defect was 0.0305 U. Now I could convert this to kilograms, and I could plug it into E equals mc squared and do a whole bunch of other stuff, or I could just use my nice conversion. One universal mass unit equals 931 MeV. And if you calculate that out, you will get these answers, depending on which units you want to use. 28.3955 MeV, or, I'm going to round a little bit here, 2.84 times 10 to the 7th electron volts, or 4.54 times 10 to the negative 12 joules. I'll leave it to you to do that math and prove that those are all the answers in different units. Let's focus on the joule one for a second. That seems really small. And it is. That's a pretty small unit. However, that's the amount of energy. This is the exact reaction that takes place in the sun. We form helium, releases some energy, this much. We say that the sun is powered based on these reactions. You might say, well, that's a tiny amount of energy. You've got to realize that in the sun, this reaction is happening not even billions, not even trillions. We're talking like 10 to the 21st times per second. I don't know if that's the actual number, but it's a huge number. Okay? This reaction of creating helium is happening so many times per second that it takes this tiny little amount of energy, you multiply that release by a number you can't even imagine, and we have the sun. We have something that can power all of our energy, that can supply all of our energy needs here on Earth, and then some. Okay? Key points for today. Mass is the same as energy. We can convert one form to the other. We know that they're related because of E equals mc squared. We can use that if we are given a mass in kilograms or an energy in joules. If we are given an energy in eV, electron volts, or mega electron volts, or a mass in universal mass units, we simply use the conversion on the front of the reference tables. That's it for today.